you could all see the screen. Can you see?
Yes, Ram.
Ramanujan graphs on that?
Yes.
Okay, that's good.
It's perfect.
Firstly, let me begin by congratulating Kalyan Chakraborty. I think I've known Kalyan since the days that he was doing his PhD in Chennai, and I believe we all stayed in the same housing complex in Besant Nagar in Chennai back in I think 1984, 85. And I still fondly remember those days when we would walk along the beach and share stories and also share breakfast. It was a very grand time, and I'm very happy to see Kalyan now take over the directorship of the Kerala School of Mathematics. And I'm also very happy to see the small image here of the seminar hall. I remember that hall. I think I was there last year. It's a nice place and brings back lots of memories, and hopefully this virus will disappear and we will all be able to travel around the world and be able to meet and get together in person. But until then, I think we have to marvel at much of the wonders of technology, especially the fact that I'm sitting here halfway around the world, and I'm able to talk to you halfway around the world and share with you some ideas about mathematics, which are very interesting to me, and hopefully they'll be interesting to you as well. And you'll be able to learn these things, because there's no greater gift than the wonder of knowledge. So let me begin by talking about Ramanujan graphs, give you definitions. Graphs actually are interesting in their own right. You should think of the mathematical concept of a graph as profound and significant as the discovery of the concept of zero. The concept of zero, as you all know, is a fundamental concept that essentially gave birth to all of mathematics. And similarly, a graph is something which is a representation of a very complex process. And through this representation of this complex process, we're able to understand the process and perhaps control the process. And if some of you have heard my talk on the weekend in the Pi Mathematics Association, I spoke about the pandemic and how mathematics can be used to control the pandemic. And there again, we have applications of graph theory and of course, first-year calculus. This talk is no different. So let's begin with the basic definition. So let's start talking about not any old graph, but I want to talk about a regular graph. A regular graph is a graph in which all the vertices have the same degree. So a graph is usually denoted as a pair of a vertex set V and an edge set E, and it's said to be k-regular if all the vertices have degree k. And to this graph, we can associate an adjacency matrix, which is a V by V matrix. It's a 0-1 matrix. It need not be. We will talk about variations on the 0-1 matrix later on in this talk, but it's essentially at the beginning, we can think of it as a 0-1 matrix. You're at the AB entry, you put 1 if A and B are connected by an edge, and you put 0 otherwise. Later on, we will talk about assigning a plus or minus ones to edges. That'll come much later, but for the time being, we can just think of the adjacency matrix in this simple fashion. The idea of associating a matrix to a graph reduces sometimes graph theory problems to linear algebra. And then we can go backwards too. So taking facts from linear algebra, we can get information about the graphs as well. Now, the adjacency matrix of a finite k-regular graph has k as an eigenvalue, because if you take the column vector, which consists of all ones, and you just make the computation, aj is equal to k times j. I'm sure you can all see that mentally. If not, I'm sure you'll be able to work that out, because the degree of every vertex is k, you see, so that's why it turns out that aj is kj. And now looked at from a linear algebra perspective, what is this saying? This is saying that if I have a k-regular graph, then k is an eigenvalue with eigenvector j. That's what it's saying. That's an interesting fact already. So k is an eigenvalue of A with eigenvector j. In this talk, I want to focus on a certain special class of regular graphs called Cayley graphs. These graphs are named after Arthur Cayley, who I suppose is one of the first mathematicians to realize the importance of groups and to study group theory in its own right. And there again, in trying to understand finite groups, Cayley came up with the idea of trying to represent the group with a graph. So let G be a finite group and S be a subset of the group G. We're going to look at special subsets such that if X belongs to S, then so does X inverse. I'm going to write my groups multiplicatively. So X inverse is the inverse element of X. And we'll construct this graph as follows. The vertices are going to be the elements of the group. And two vertices A and B are going to be adjacent if I have an element X in my set capital S, such that AX equals B. And because I impose this condition that if X belongs to S, so does X inverse, you can see that if AX equals B, then A equals BX inverse. And therefore, these are undirected graphs. You did not, by the way, study undirected graph. We don't need to put that assumption in. I put that in for convenience. We'll find out later. I mean, if you study these graphs in detail, you can remove that and still study these graphs and come up with a viable theory. Now, we want to discuss what's called the spectrum of the abelian Cayley graphs. When we talk about spectrum of a graph, we mean the eigenvalues of the adjacency matrix attached to the graph. That's what's called the spectrum of a graph. And as you know, if you are given a matrix A, the eigenvalues tell you a lot about the matrix. And so the idea here is, if I know the spectrum of the adjacency matrix, can I say something about the graph? Now, if G is an abelian group, it's not difficult to show that the eigenvalues of the adjacency matrix have the following elegant description. If you take an irreducible character chi, and you sum chi of S, where S ranges over all the elements in capital S, then these are the eigenvalues of the adjacency matrix. And if you want to check what the corresponding eigenvectors are, the eigenvectors are explicitly given as these column vectors, chi of G, where chi ranges over the characters. So I've actually given you the answer. If you take that column vector and compute the what happens to this column vector when you hit it with the adjacency matrix, you will get this lambda chi as the eigenvalue will pop out. And so in some sense, by telling you what the eigenvector is, I've essentially proved the theorem. So you may want to think about that if you haven't seen this stuff before. Now, that's the spectrum if I have an abelian group, an abelian Cayley graph. What happens if I have a non-abelian Cayley graph? If I started with a non-abelian group, what are the eigenvalues of the adjacency matrix? And this is an interesting question in its own right. And it turns out that I can't believe this, but there are 5 people who rediscover the same theorem in a short span of about a decade or so. I can't believe this, but it's true. So if we assume further that S is stable under conjugation, there's a nice description of the spectrum due to various. Laszlo seems to be the first person who discovered this, as far as I can tell. Maybe somebody else did, but who knows? But certainly 1975 is the earliest paper I could track. After that, there's a paper written by Babai in 1979, also unaware of the paper of Lovash. And then there's a paper by Diaconis and Shashahani in 1981, again, unaware of these earlier papers. And then finally, there's a paper by Ji Shang, I hope I pronounced his name correctly, Ji Shang, 1988, where again, he derives this answer and seems to be unaware of the earlier work. Obviously, it's an important theorem. It's been discovered by so many people. So if G is a finite group, S is a symmetric subset which is stable under conjugation. That means if I conjugate an element, then it's still in the set. Then let A be the adjacency matrix of this Cayley graph. Then the eigenvalues are given now by these character sums, summation chi of S, divided by the character degree. And here, the chi ranges over all the irreducible characters. And moreover, the multiplicity of the eigenvalue, lambda chi, is chi of 1 squared. Now keep in mind, our group G has, let's say, size n, and therefore there are n vertices in the graph. And the adjacency matrix, therefore, is an n by n matrix. And therefore, by linear algebra, the adjacency matrix has n eigenvalues. Here they are. The multiplicity is chi of 1 squared. And as you know from your basic group theory, summation chi of 1 squared, as chi ranges over all the irreducible characters of the group, is equal to the order of the group. So here we are. These are all the, it's a beautiful theorem. As far as I'm aware, this theorem is not as simple to prove as the previous proof I gave you for the abelian Cayley graphs. And for this, you have to really know some representation theory, and you need to know something about the regular representation, how it decomposes in the group algebra. So what are the eigenvalues of a K-regular graph? For any finite graph, it's easy to show that all the eigenvalues of the adjacency matrix are bounded by the maximal vertex degree. So the Cayley graphs are a special class of regular graphs. But now I want to look at, more generally, K-regular graphs. So all the eigenvalues of a K-regular graph are bounded by K. We already figured out that K was an eigenvalue. The largest eigenvalue is K, and all the other eigenvalues are bounded by it. That's not hard to prove. I'll leave that as an exercise. If you don't know any graph theory, by the way, these are all very simple things to prove. And then it turns out that a graph is bipartite if and only if the eigenvalues of the adjacency matrix are symmetric about 0. Now, the easiest way to see that is by noticing that once you have the eigenvalues, you have information about closed cycles. And in a bipartite graph, there are no closed odd cycles. And since the sum of the kth powers of the eigenvalues is the number of closed k cycles, you see that has to be this way. Now, and so bipartite K-regular graphs, bipartite graphs in general actually have symmetry about eigenvalues are symmetric about 0. So if we already realize that a K-regular graph has K as an eigenvalue, so if it's a bipartite K-regular graph, then minus K is also an eigenvalue of its adjacency matrix. So for a K-regular graph, any eigenvalue lambda whose absolute value is K is called a trivial eigenvalue. All the other eigenvalues are called non-trivial. So what is a Ramanujan graph? For any K-regular graph, we will define lambda of x to be the maximum of absolute value of all the non-trivial eigenvalues. And a graph is called Ramanujan if this lambda of x is less than 2 square root k minus 1. Now, why 2 square root k minus 1? Well, that's a very good question and has actually a profound answer. And hopefully part of that profundity will emanate through this discussion. What Ramanujan has to do with these Ramanujan graphs will be explained later. Now, Ramanujan never worked in graph theory. But it turns out that the study of Ramanujan graphs involves some of Ramanujan's work. So here's some simple examples of graphs and eigenvalues. So here's what's called the complete graph on 5 vertices, K5. Then we have the bipartite graph on 3 vertices, K33. And if you calculate the adjacency matrix of the complete graph on 5 vertices, you see that, of course, we already agreed it's a 4 regular graph. Therefore, 4 is an eigenvalue. So 4 to the power bracket 1 means 4 is an eigenvalue with multiplicity 1. And minus 1 to the power bracket 4 means minus 1 is the other eigenvalue. It has multiplicity 4. And therefore, by my definition, all the non-trivial eigenvalues have absolute value 1. And it certainly is a Ramanujan graph. And same thing with the K33. It has largest eigenvalue 3. And it, by symmetry, it has minus 3 as an eigenvalue 2. And the other eigenvalues are all 0. So these are all Ramanujan graphs. These two particular graphs, K5 and K33, are famous because of the classification of planar graphs. As many of you may know, a graph is planar. That is, a graph can be drawn on the plane so that no two edges intersect one another, if and only if it is not edge contractible to either K5 or K33. Now, in childhood, you may have encountered K33, this particular graph K33. You may have encountered that. It's this famous problem of the utility connections. So the vertices on the right-hand side, these 3 vertices are 3 houses. The vertices on the left-hand side are the utilities, water, electricity, and gas. And you're supposed to connect these utilities to the houses in such a way that the connections don't cross each other. You may have seen this problem in your childhood. It's a nice way to occupy the attention of a bratty 5-year-old. It turns out that this can't be solved. It can only be solved on the torus. So this is not a planar graph. There's no way you can connect the 3 vertices on the left-hand side with the 3 vertices on the right-hand side without having the edges cross one another. So those are examples of Ramanujan graphs. Here's some more examples. This is the K7 complete graph, which is 6 regular. All the non-trivial eigenvalues of K7 again are equal to -1. And it's again Ramanujan. In general, the complete graph on n vertices. So what's the complete graph on n vertices? And you have n vertices and you join every vertex to every other vertex. Complete graph. And one can show again all the non-trivial eigenvalues are equal to -1 with multiplicity n -1. Now, the Peterson graph, I threw this in as a joke, but anyway, the Peterson graph is Ramanujan. So here's the Peterson graph. It's a 3 regular graph with 10 vertices. And its characteristic polynomial is lambda -3, lambda + 2 to the power 4, lambda -1 to the power 5. And again, check that indeed all the non-trivial eigenvalues satisfy lambda less than 2 square root 2. Remember here, it's a 3 regular graph. So K is 3, 3 - 1 is 2. So 2 square root K - 1 works up to be 2 root 2. And it is indeed the case. It's named after Julius Peterson, who is not the Peterson of the Ramanujan-Peterson conjecture. I just was trying to make a joke. You know, the generalization of the Ramanujan conjecture, which will appear later on in this talk, is connected to the theory of modular forms. And there's the famous conjecture, Ramanujan-Peterson conjecture, but that Peterson is not the same as this Peterson. But I thought it was nice that this Peterson's graph turns out to be Ramanujan. So why are Ramanujan graphs important? Well, that's a question which will be discussed now and will also be discussed perhaps at the end of this talk. To answer this question, we can look at Ramanujan graphs from a variety of angles. For the time being, let's look at it from the standpoint of what's the diameter of a connected graph. Given a connected graph X, the distance between two vertices is defined to be the length of the minimal path from X to Y. And the diameter of a graph is that the maximum value of this distance function. Okay, so that's the idea now is that the diameter, in some sense, if you think of a graph as modeling a communication network, then you see that the distance function tells me how fast I can go from point A to point B. Obviously, if you're designing a communication network, you want to have the fastest possible means of communication. So you want to minimize the distance function. I'm just wondering, are all the microphones off? If someone can make sure that all the microphones are off, that'll be good. Except mine, of course, which was not a good idea. Okay, so the diameter graph is the maximum value of the distance function. So there's a famous theorem in 1989 discovered by Fan Chung, and she proves the following theorem. If X is a k-regular graph with n vertices and diameter m, the diameter is bounded by essentially log n divided by log k over this lambda of x. Remember what lambda of x was? It was the maximum absolute value of all the non-trivial eigenvalues of x. Now, I told you that the idea behind communication network is to make the diameter as small as possible. So you want to make this quantity log n over log k over lambda as small as possible. In order to do that, you want to make the denominator as large as possible. But the denominator is log k over lambda, and therefore that means you want to make lambda of x as small as possible. And therefore, Ramanujan graphs are going to be the answer to that question. So the implication of Chung's theorem is to minimize the diameter, we need to maximize the denominator, and to maximize the denominator, we need to minimize lambda of x. So this is useful in constructing efficient communication networks. And for instance, the vertices can represent cities, and the edges will be communication lines between them. And we want to fix the degree. Why do we want to fix the degree? Because you want to fix the number of communication lines. You don't want to have too many communication lines, but you want to minimize the number of communication lines because that's hardware. Communication lines are hardware, and you want to minimize the use of hardware, and that's why you want to minimize the diameter. Now, recently, there's also been excitement in using this theorem in the study in neurology, where to study the brain, the neurons are the vertices and the synapses are the edges. And it turns out, apparently, according to all the findings in neurobiology, that the neural network forms what's called an expander graph. And Ramanujan graphs are special cases of expander graphs. So it seems that the brain knows something about Ramanujan graphs. So there's a famous theorem by Noga Elon and Ravi Bupana called the Elon-Bupana theorem, which tells us why Ramanujan graphs are important. If you look at this maximal non-trivial eigenvalue, they can produce infinitely many families in which that absolute value is at least 2 square root k minus 1. Now remember, in trying to construct Ramanujan graphs, we want to minimize lambda. So the Elon-Bupana theorem tells you that, well, you can't do better than 2 square root k minus 1. That's the best you could do. And so now the significance of the Ramanujan graphs becomes important because that's the limit. So to minimize lambda of x in Chung's theorem, best we can go for is 2 square root k minus 1. In other words, the minimal diameter is achieved through Ramanujan graphs. Now, so you're trying to construct these k-regular graphs with these optimal properties. And because we discussed how group theory can be used to construct k-regular graphs, we could try to use k-leaf graphs to construct them. Now, if you try to use the abelian Cayley graphs to construct Ramanujan graphs, it's not easy. Abelian Cayley graphs are rarely Ramanujan. In 2006, myself, Joel Friedman, and Jean-Pierre Tillich proved the following theorem. Let d be a positive integer and let mu be in 0, 1. Then for any d-regular abelian Cayley graph on n vertices, the second largest eigenvalue is already pretty close to d. So I'm sorry, I'm using d, but I just copied and pasted from my paper. So in the paper, we use d for the degree, but I'm sure you can make the mental translation. So it tells you that if you try to use abelian Cayley graphs, that second eigenvalue, the second non-trivial eigenvalue, gets asymptotically close to the first one. So abelian Cayley graphs are not the way to do it. That's a paper in Journal of Combinatorial Theory, Series B in 2006. So you have to look at non-abelian Cayley graphs. And so the first people who seem to have done that are Lavotsky, Phillips, and Sarnak. In 1988, they proved the following theorem. If k is one more than a prime, p a prime, then there's a sequence of k regular graphs, xn, with xn going to infinity. Sorry, I should have made this sentence accurate. Of course, there's a I forgot to finish the sentence. If k is p plus 1 with p a prime, then there's a sequence of k regular graphs xn with xn tending to infinity, which is Ramanujan. Sorry about that. So these are all Ramanujan graphs. That is the point. I mean, as I stated, unfortunately, it's not accurate, but there's a sequence of Ramanujan graphs that satisfies this property. And the proof of this theorem used the Ramanujan conjecture about eigenvalues of Heck operator acting on the space of cusp forms of weight 2. Now, this conjecture was proved by Eichler and Shimura in the 1950s, and the generalization of the Ramanujan conjecture to higher weights was proved in 1974 by Pierre de Lille. Now, the Lavotsky-Phillips-Sarnak theorem was also proved independently by Margulis, but it seems that Ihara was the first person to see the importance of these graphs in 1968, and in some sense, point the world's attention toward the importance of these graphs. Now let me explain the LPS construction. So they take two primes p and q, which are congruent to 1 mod 4. And a classical theorem of Jacobi tells us that there are exactly 8 times p plus 1 solutions a, b, c, d, such that a squared plus b squared plus c squared plus d squared is p. Now, all of you know the famous theorem of Lagrange, that every natural number can be written as a sum of 4 squares. But the theorem of Jacobi is a determination of how many representations there are. And for that, Jacobi uses the theory of modular forms. In fact, the subject of modular forms arises in a serious sort of way for the first time in Jacobi's work. And they're exactly 8 times p plus 1 of them. So among these, they're exactly p plus 1 with a positive, b, c, d even. So if we take away these signs and all that, if you insist that a is positive and b, c, d are even, they're exactly p plus 1. And to each such solution, we're going to associate a matrix a plus ub, c plus ud, minus c plus ud, a minus ub. Here, u is a solution of u squared equals minus 1 modulo 4. I seem to have forgotten to say that. So so that's why we take these primes congruent to 1 mod 4. So most of you know, or all of you know, that when you have a prime congruent to 1 mod 4, you like q is a prime congruent to 1 mod 4, you could solve u squared equals minus 1 mod q. In other words, minus 1 has a square root mod q. And you can use that to construct this matrix V tilde. So this gives us p plus 1 matrices in the group PGL2Z mod QZ, and we let S be the set of these matrices. And it turns out that the Cayley graph, XGS, is a Ramanujan graph as we vary Q. So this is the explicit construction of P+1 regular Ramanujan graphs. Now, the Ramanujan conjecture, which I kind of alluded to earlier, was first enunciated in 1916. He wrote a fundamental paper which shaped the development of number theory in the 20th century. In this paper, he introduced the tau function. So most of you know that the tau function can be defined without talking about modular forms at all. You just take the infinite product q times product n going from 1 to infinity, 1 minus q to the n to the power of 24, expand it, and you get these numbers, tau n. And Ramanujan found that these numbers really had remarkable properties. For example, he noticed that if you take minus 24 and multiply by 252, you end up getting the coefficient of the sixth term here. And so there was a multiplicative relation amongst the coefficients. And he made his famous conjectures. And one of the famous conjectures was that mod tau of p is less than 2 p to the 11 halves. Peterson generalized this. Notice this Peterson has 2 S's and the other Peterson had only 1. He generalizes to eigenmodular forms of arbitrary weight, and the person who proved all these theorems is Pierre de Lin as a consequence of his proof of the Weil conjectures. So here he is talking about special values. If you can see the blackboard there, it's talking about special values of the Riemann zeta function, and in general, trying to connect the Lefschetz fixed point formula to zeta 2k. Now I want to talk about the work of Ihara. Remember, I told you the work of Ihara precedes the work of Lubotsky, Phillips, and Sarnak, and Margulis. And Ihara was the first person to introduce what's called the zeta function of a graph. So given a graph X, let n of r be the number of closed paths in the graph of length r, such that neither c nor c squared have backtracking. So you want to go from a point A along the graph, and then you want to come back to that point, but you're not allowed to backtrack. That's all. And forget about the tails, but that's basically the idea. You're not allowed to backtrack. So these are optimal. You're not, if you wanted to take a path, without backtracking, you count the number of such closed paths. These are called geodesics in the graph. And the Ihara zeta function of a k-regular graph is a power series, exponential, summation n sub r t to the r over r. For those of you who are familiar with algebraic geometry, you know that if you take a curve C over a finite field, you can look at the number of points n sub r of the curve over the finite field of q to the r elements, and the zeta function of a curve over a finite field is exactly something like that. So this is very analogous to the zeta function of a curve over a finite field, except there's no finite field here, and there's no curve. But the analogy is striking. And it turns out that Ihara noticed this for the first time. If you put q equal to k minus 1, so I've got a k-regular graph, and put q equal to k minus 1, change the t in the power series to q to the minus s. Then it turns out that this zeta function has singularities on the line real s equal to half, if and only if the graph is a Ramanujan graph. In other words, the analog of the Riemann hypothesis is true for this k-regular graph zeta function, if and only if the graph is a Ramanujan graph. Now, this discovery I consider of paramount importance. It reminds me of the metaphor that Andre Weil used in his 1949 paper when he enunciated his famous Weil conjectures. The idea of 3 parallel universes. On the one hand, you have zeta functions of number fields, which is the classical setting, the Riemann zeta function, the Dedekind zeta function, and things like that, Art and L series. Then you have zeta functions of curves over finite fields, for which the Weil conjectures are generalizations. And then now you have this other world, zeta functions of regular graphs. So these are 3 parallel universes exhibiting remarkable similarities. And it seems that one should probably study each universe in its own right and see the interconnections. Perhaps we can understand the universe that we're really interested in, with data functions of number fields. Perhaps we can understand them better by studying these other two worlds. So question is, can we construct Ramanujan graphs when k plus 1 is not a prime number? So in 1994, Morgenstern used algebraic geometry in Grünfeld's work on the analog of the Ramanujan conjecture for function fields to construct infinitely many Ramanujan graphs when k plus 1 is a prime power. This paper was also published in the Journal of Combinatorial Theory, Series B, in 1994, and anybody who wants to understand Grünfeld modules and see them used in a powerful sort of way, I recommend this paper. This paper is not too long. It's about 20 pages, and it's very readable. Now, so the problem has been solved when k plus 1 is a prime or k plus 1 is a prime power, and the question arose whether or not one can do this for other k's, which are not primes or prime powers. And so about 20 years ago, my student Sebi and I thought about constructing what are called almost Ramanujan graphs. In 2008, we proved this following theorem: fix an epsilon positive for almost all values of k in the sense of natural density. There are infinitely many k regular graphs, such that all the non-trivial eigenvalues of x are an absolute value less than 2 plus epsilon square root k minus 1, and then you can actually construct them. There have been probabilistic results of a related kind proved by Joel Friedman, who I mentioned earlier, but those are probabilistic. Here are constructive families, and our paper appeared in Forum Mathematicum in 2008. So the idea of the proof is quite simple. If you want to construct a k-regular Ramanujan graph when k is close to a prime p, well, the idea is you take your p plus 1 regular Ramanujan graph, given by the Lubotsky-Phillips-Sarnak construction, and then proceed to make it k-regular by carefully adding edges. You know, you want to make it k-regular. There are already p plus 1 edges coming out of each vertex. You want to add k minus p minus 1 edges to each vertex to make it k-regular. And then you want to kind of control the growth of the eigenvalues. And that's when Hermann Weyl's theorem helps us to understand how things change. This is a beautiful theorem in linear algebra. If you haven't seen it, I would suggest you look at it and study it. It's a beautiful theorem. It tells you how our eigenvalues change when you add matrices. So if I started off with a real symmetric matrix A and B of order n, then the ith eigenvalue, they're real symmetric matrices, therefore all the eigenvalues are real, and then you can order the eigenvalues as an increasing sequence, and so you have the ith eigenvalue of A plus B is trapped between the ith eigenvalue of A plus the first eigenvalue of B, and the nth eigenvalue of B plus the ith eigenvalue of A. So there's a kind of a control theorem on the eigenvalues when you modify the matrix. So what does carefully mean? So carefully means you have to get hold of a matching. Matching is an important idea in mathematics, in combinatorics, and it appears here. It'll appear later on when I discuss the recent progress of Ramanujan graphs as well. The matching P in a graph X is a set of mutually disjoint edges. That is, the edges do not have any common vertex. A perfect matching is one in which all the vertices are paired up. The idea is to look for a perfect matching in the complementary graph of the given Ramanujan graph. So if given a graph X, you can talk about the complementary graph. The complementary graph is the same vertex set, but two vertices are now adjacent in the complementary graph if they were not adjacent in the earlier graph. And the adjacency matrix of a perfect matching on two n vertices is a permutation matrix whose eigenvalues are 1 and -1, each with multiplicity 1. So now the adjacency, so how do we modify our regular graph? We're going to throw in this matching permutation matrix, and then each time we throw a permutation matrix, the eigenvalues are being changed by +1 or -1. So you're able to control that. And then using the Herman-Weyl theorem, we're able to find the final thing. Now, the question is, how do you find the matching? So there's a nice theorem of Choba, Gregory, and Himmer's that says that if the third eigenvalue is bounded by essentially k over 2, remember k is it's a k regular graph. If the third eigenvalue is bounded by essentially k over 2, then X has a perfect matching. And then using that perfect matching, you can take your Ramanujan graph and then modify it carefully using the matching and then control the eigenvalues. So starting with the Lubotsky-Phillips-Sarnak-Ramanujan graph, the complementary graph satisfies the Choba-Gregory-Hamer's condition. And one can find a perfect matching, which by Weyl's theorem then leads to a new graph, which is k plus 1 regular graph. You started with a k regular graph, now you've got a k plus 1 regular graph, and the eigenvalues, the non-trivial eigenvalues, are now bounded by lambda plus 1. So you've only increased the size of the eigenvalue by 1. So this is the idea behind this thing. And now the question then arises, if you're going to take a Ramanujan graph that Lubotsky, Phillips, and Sarnak constructed for primes, well, then the values that you're going to be able to do this for are the values in which are close to primes. So the question about gaps between consecutive primes now becomes important, and this is another cosmos in its own right. Let P sub n be the nth prime. In 1937, Harold Kremer made a conjecture that Pn plus 1 minus Pn is O of log squared Pn. That means the gaps between consecutive primes is not too big. If this conjecture is true, then when we proceed using our construction, we find that you can construct almost Ramanujan graphs for any degree d. Again, I made a typo here. This d should not be d, it should be k. For any degree k, lambda of x has got to be less than 2 square root k minus 1 plus an error of O of log squared k. So it's not too bad. This is not a bad theorem if the Kremer conjecture, of course, is true. Now, it turns out the Kremer conjecture is true kind of with probability 1, so you can kind of use that to construct many graphs. But what is known unconditionally, the Kremer conjecture is not known, so Pn plus 1 minus Pn is O of Pn to the power of 0.525, and this is the theorem of Baker, Harman, and Pintz. Now, this may have been improved. I haven't been keeping up with the latest world records on gaps between consecutive primes. So my apologies if anyone who has improved this result is listening. But anyway, the idea is, I don't think the half is done. The Riemann hypothesis would imply something like half plus epsilon. So it turns out, using a density argument, you can prove something like this: Pn plus 1 minus Pn is less than epsilon root Pn, as I mentioned already. This is sufficient for our purpose. I'm sorry, this D shouldn't be there. Now, in 2013, Yitang Zhang proved that Pn plus 1 minus Pn is bounded by 70 million for infinitely many n. This is a remarkable breakthrough in analytic number theory. Tells that this happens infinitely often, so this is very interesting. And then this was improved later by Maynard and Tao 1 year later. They showed that Pn plus 1 minus Pn is bounded by 246 for infinitely many n. As far as I'm aware, this has not been improved. The twin prime conjecture tells you that Pn plus 1 minus Pn is less than 2. Here again, we see that the world of prime numbers, classical analytic number theory, has something to say about explicit construction of Ramanujan graphs. Now let me discuss in the time remaining the most recent work of Marcus, Spielman, and Srivastava. In 2013, they showed there exist infinitely many bipartite Ramanujan graphs for every degree. So their paper appeared in the Annals of Math, and it's non-constructive, but reasonably elementary and elegant. Now, if there are graduate students listening, I would recommend you study this paper. It can easily be mastered within a month's time, because the tools that are needed in the proof are not beyond, first year calculus and first year linear algebra. So let me, because it's so elegant and it's so elementary, I want to discuss the main ideas of this paper. A key concept in this paper has to do with what are called two-lifts of graphs. What's a two-lift? This was introduced by Bilou Lineal in 2004. I believe this is not Yuri Bilou, who does algebraic geometry, number theory, but I think it's a graph theory, Bilou. I suppose Bilou is a common name. Given a k-regular graph G, consider any two-lift G star of G. Then the spectrum of G star is the union of the spectrum of G and the spectrum of the corresponding signed adjacency matrix of G. So let me try to explain this. There's a lot of stuff here. So if I have a graph X and UV is an edge, then I'm going to construct another graph X hat. The number of vertices in X hat will be double the number of vertices of X. Okay, so you just double. So for each vertex U, you will write U0, U1. Each vertex V, you will write V0, V1. Now, either you will make U0 adjacent to V0, U1 adjacent to V1 and leave it like that, or you will cross them. U0 adjacent to V1 and U1 adjacent to V0. So you're allowed for each adjacency relation in the lower graph. In the upper graph, you either have this picture or this picture. So now you can see that you can create tons of these lifts, one for each, two choices for each edge. So you get lots of. So it turns out that for any other lift, the spectrum of G star, remember G star has double the number of vertices. And so it's got double the number of eigenvalues. And the beautiful theorem is that the eigenvalues of the new lift is the union of the eigenvalues of G along with the signed adjacency matrix of G itself. So now we go back to the adjacency matrix. I'm sorry, I'm using G here and X here, but I think you can make the translation. So if you're looking at the adjacency matrix of X, we said that you put in the ij entry, you put 1 if I is adjacent to J. Well, now you will put +1 if this is the lift that you've chosen, and you will put -1 if this is the lift that you've chosen. So you now end up taking the adjacency matrix of your old graph X, which is still n by n matrix, and it's now been tampered with. You've changed the signs. It's called the signed adjacency matrix. And so the spectrum of the signed adjacency matrix is called a set of new eigenvalues. And it turns out that they made a conjecture at the end of their paper. They said if G is Ramanujan, they conjectured there's always a two-lift that's also Ramanujan. That's an impressive, it gives you a program. See, now it gives you, we already saw at the beginning of this lecture that the complete graph on n vertices is always Ramanujan. And therefore, you take the two-lift of the complete graph according to their conjecture. This is a conjecture. According to their conjecture, there's a two-lift that's Ramanujan. So take that one, now repeat the process. And every time you keep getting, a K, by the regularity of the graph is still preserved in this process. So this is the main theorem used, I should say, this is the main theorem used in the MSS paper. The bilineal, and so what they do is they prove the bilineal conjecture for a special class of graphs called bipartite Ramanujan. So if you take a bipartite Ramanujan graph, then you see that simply by taking the complete graph and taking successive two-lift, you still are fine. So what are open questions and directions for future research? Well, problem one is their construction is existential. So you'd like to give a constructive method for constructing infinitely many Ramanujan graphs of every degree. Is it possible to modify our proof using gaps between primes and use averaging techniques to determine optimal Ramanujan graphs in construction? Now, much of the work of the Lubotsky, Phillips, Zarnack, and Morgenstern has been extended to hypergraphs and complexes and buildings, most notably by Winnie Lee and her students. And so again, the question is, can some of this work of Winnie Lee and her students be generalized to this setting? These are all problems for research. I mean, these are all things that people haven't worked on. I think it's worth working on, because you see there, as I said, there are many different worlds of mathematics. Some are number theorists, some are geometers, and some are graph theorists. And again, it's like these parallel worlds where the more you can interact, the better it is for the subject and probably for yourself. So these two lifts of graphs, as I mentioned, was introduced by Bill Liu and Linda in 2006. And I already told you how the adjacency matrix AS is collected, and it turns out that all the adjacent eigenvalues are the union of the eigenvalues of these two things. Now, they conjecture that every K regular graph is a two-lift, which all the new eigenvalues are at most 2 K minus 1. That conjecture is still open, but if true, would have given you the solution. But now, in order to solve the problem, you have to go to the bipartite graphs. So that's what they do. They look at the bipartite things. And I think I'm going to kind of go fast a little bit, but essentially this is not very difficult. By looking at the bipartite graphs, they're able to control. Remember, the bipartite graph, the eigenvalues come in pairs, plus and minus. There's a symmetry about the origin. Therefore, that can be exploited and kept things under control. And another important key idea in their paper is the idea of a matching polynomial. So if I have a graph X, I already talked about matchings, but this time we want to count the number of matchings consisting of I edges, and let m sub I be this number. Then you define this matching polynomial. Minus 1 to the I, m sub I, lambda to the n minus 2i. So this is a nice polynomial, something like the adjacency characteristic polynomial or chromatic polynomial of a graph is the matching polynomial. And it turns out that the expected value of all the adjacency matrices, you have for each edge, you're going to assign, you're taking a two lift. And so depending on which lift you took, you're going to put a +1 or -1. And so you have all these signed matrices, and it turns out that the expected value of the adjacency characteristic polynomial of the signed adjacency matrix turns out to be the matching polynomial. This theorem, by the way, which is very critical, is very easy to prove, but I will not prove it. Simply because I'm running out of time. The Heilmann-Leib theorem says all the roots of the matching polynomial have absolute value at most 2 square root k minus 1 if the graph started with a maximal degree k. This is a beautiful theorem. Now, to understand graphs, you really have to understand trees. And what is a tree? A tree is an acyclic connected graph. And if you have a bunch of acyclic connected graphs, it's called a forest. So with that terminology in mind, Gottsel noticed that in order to understand a graph X, you can construct what's called the path tree. And then he proved that the matching polynomial of the graph divides the matching polynomial of the path tree graph. And what's so great about that? Well, the matching polynomial of a tree is the same as the characteristic polynomial of the adjacency matrix. And then these guys tell you that, that you have absolute value 2 root k minus 1. Therefore, you're in business. So the characteristic polynomial of tree is the matching polynomial of the tree. And it's not easy, it's not difficult to prove. I will suspend this slide. It's, as you can see, it's nothing but linear algebra done correctly. And then you see the theorem once you set it up correctly. And the spectrum of a tree, if T is a tree with a maximal degree K, all the eigenvalues, lambda of T, satisfy modulus of lambda less than 2 square root K minus 1. I was actually going to prove this in this thing. Here's the short proof, simply because there doesn't seem to be a neat proof in the literature. And I came up with this kind of elegant proof. When you try to prove it, you end up getting a bound for the eigenvalues. Lambda satisfies delta plus K minus 1 over delta, but delta now you can choose delta to be anything. And now the optimal solution to this bound is delta equal to square root K minus 1. There is bingo. You get your 2 root K minus 1 this way. So that's how the proof is all put together. And then you have to study basic first-year calculus, where you study what's called interlacing polynomials. Again, I think I better rush through this quickly. It's not difficult. It's essentially, the idea is to understand, if I have a bunch of polynomials with real roots, where are they moving about when you add them together? And so if you kind of do basic first-year calculus and just see what's going on, the proof, as you see, is not very difficult. You can control the eigenvalue or the zeros of these polynomials. And so the final proof is completed by looking at the eigenvalue of the sum of the polynomials. Remember, I told you this sum is the same as the matching polynomial. And so now the idea is that there is a signing. There is a signing for which the eigenvalue of f is bounded by the largest eigenvalue of this. The largest eigenvalue of the matching polynomial is bounded by 2 squared K minus 1, and therefore you're done. So that's basically the proofs. Now, if I'm able to give you this proof, even rush through this proof in an hour, you can see the proof is highly accessible to any graduate student who wants to study this proof in earnest and perhaps come up with some new ideas. So let me complete this talk by talking a little bit about expander graphs. Ramanujan graphs form an important subset of a larger collection of regular graphs called expander graphs. And the technical definition of an expander graph is that you take a subset, for each subset S of vertices, you look at the collection of edges that connect you to the complementary set. And you look at the how many edges are going out of one set into the complementary set. And this quotient determines the expansion of the graph. So if X is a K-regular graph, the expansion constant is again controlled by that spectral gap, as we talked, lambda of X, which is this largest absolute value of the largest non-trivial eigenvalue. So the implications of this study of expander graphs to neurobiology has been quite significant. And in many ways, I mean, implications to expansions of consciousness. If you think of vertices as neurons and edges are synapses, the edge expansion constant is determined by how many synapses exist between a set of neurons and its complementary set. So this is really the meaning of study or swadhyaya in yoga, because you're trying to connect one idea with another idea through the process of reflective consciousness. And so the idea of expanding consciousness is actually suggested by this expander graphs. So here are some of the basic references. I wrote a paper almost 20 years ago on Ramanujan graphs. That paper is a bit outdated because at that time there was this recent work was not there. These papers by Sebi and myself and Joel Friedman and Jean-Pierre Tillich is also accessible and can be studied by any graduate student. And the paper I already mentioned by Marcus Spielman and Srivastava appeared in the Annals of Math in 2015. And the paper on which I am basing this particular talk, which is an expository talk in which some of the slides I used, in which the proofs have been given, will now soon appear in the new journal called the Indian Journal of Discrete Mathematics. So thank you very much for your kind attention. I wish you happy holidays and a very happy New Year.
Thank you so much, Professor Ram Murty. So we have quickly, there is a question, a couple of questions. So quick, because Filippo is waiting.
Sir, can you just remind me what your theorem was regarding construction of almost Ramanujan graphs? Like there was some bound on lambda x, which is less than 2 plus epsilon or something. What was the exact statement?
Yeah. The exact statement is you give me a Ramanujan graph, then I can make a k regular graph, which is 2 plus epsilon square root that p plus 1. So that means you've not gotten the exact bound, but it's almost there.
So I was just
and I gave the references. You may find the references. Yeah.
I was wondering, can we somehow ensure that the lambda of x is some integer or belongs to some discrete set, so that if you can let epsilon very small, we can almost get the Ramanujan bound? Like if it's some integer.
No, I don't think. No, I don't. No, yeah, that's a good question. I don't think our method will give you Ramanujan graphs. It'll only give you almost Ramanujan graphs because, unfortunately, we don't know how to control that. Thank you for the question.
Hello, sir. So you gave the definition of a zeta function of a graph due to Ihara. So I was just wondering how the properties of the zeta function connect the cohomology or the homology of the space in which that particular graph is planar. So the definition talked about closed curves. So I was just wondering.
Yeah, no, so as far as so the question, there are two parts to your question. The graph theory version has nothing to do with étale cohomology of curves over finite fields, the graph theory version. However, there is a way to associate graphs to curves, which is what Ihara is doing in his paper. For that, of course, your question is valid. So for the graph theory world, as far as I know, there are no cohomology groups. There's no cohomological interpretation of eigenvalues.
Okay. Okay. Thank you.
Could I ask a question?
Yes.
Is there time? Very beautiful talk. A lot of interesting ideas to reflect further on. I'm just curious about this true covering, because it's clear that, as you've explained in other contexts, it's kind of introducing an algebraic topology kind of perspective on the problem. If I took a more complicated covering, say on which the instead of Z mod 2, I had some group, then would I get, can I say something, use the same sequence of logic through the matchings and then the Godzel theorem to get to trees and then estimating their eigenvalues, together with what your earlier comments about how to estimate eigenvalues of when you have an abelian K-graph of an abelian group.
Yeah.
Can you put all this together?
Yeah, that's a good question, and I believe that was just done recently. I mean, like this year or last year by, I'm not sure, there are about 3 authors, one of them being Sabin. So there is that, yeah. And you're right, there's obviously some algebraic geometric direction this can go in. Especially, and then there's a way to interpret the universal covering space of all K regular graphs as the K regular tree, which is, of course, it's got to be an infinite graph. And then that's what Ihara was doing. He was using the K regular tree as the analog, and he was using that. He was looking at that as the analog of some Selberg's construction of the zeta function.
Oh, interesting.
Yeah, so I think if there are any further questions, Ram is always available, because we have this talk of Patrice Filippo, and I see that he's already there. So Ram is always accessible to any of you, and I'm sure some of the students look at the papers that Ram pointed out and be in touch with him. Really very interesting questions relating various ideas. Thank you so much, Professor Ram. Okay, so Srijit, is there any YouTube chat question just for quick?
Yeah, there is a question.
Yes, sure.
What are Hecke operators?
Well, Yeah, that you have to read a basic book on modular forms, I would say.
Okay. Thank you, sir.
Thank you so much, Ram. It was really wonderful, and hope to see you in next summer. Don't forget that. I mean, you hope situation will improve, and you will be here, both you and Kumar.
I'll take that as a firm offer. Yes.